Swayam Prabha. Digital India. Educated India.
Hi, welcome back. So let us complete the topic that we were discussing last time. So essentially, we started out by discussing the computational cost of implementing a DNS, right? And we came up with this, so we looked at several things, right? Including experimental data, is to decide that where different modes of scales lie within a given solution domain, right? And we looked at this plot, right? So we came up with this plot where K max eta is 1.5 is the modes of motion which are dynamically significant basically lie within a sphere of radius K max. So which is what I've drawn here, okay? And in that we have these, okay, let's sort of, okay, I can't do that here. So yeah, so in that we actually have this, so radius is essentially r, okay, and this again we have another radius which is shown in green, right, which is k di, which is the limit of the dissipative range. So essentially with this, the one which is marked with yellow is the range, or is the shell in which most of the dissipative motions are available, and in the shaded region with blue, right, so that's the region where one has the inertial subrange, right, that's the energy containing zone, and the small circle right inside, that's the radius of Ke, right, that's where the peak of the energy spectra lies, right. So the maximum energy containing modes are right there, okay. So this is the domain that we are looking at, okay, and our job is to sort of calculate all these motions, right. So what we're trying to figure out here, what we're basically realizing is that if I take this domain, which is a sphere of radius K max, right, I don't have like an equal or even distribution of motions, okay. So I think here Kolmogorov's length scales become very, very important, because now we know that energy, and again, not just Kolmogorov's length scales, but also the fact that energy, how energy is being transferred, right, passed on. So therefore, so based on those, we have the length scales where, when I say dissipative range of motion, so that's the range we are looking at, and then you have inside the dissipative range also, right, where basically the energy is being converted to, mechanical energy is being converted to internal energy, right, using viscosity, but you also have a inner inertial subrange where there is, it's still the viscosity, the inertia effects are still not yet completely zero. So that lies somewhere within the blue shaded region, and of course the energy peak, some of the peak energy motions are within the small region which is Ki, right. This is something we discussed last time, and this K di, okay, so K, it's about 0.1 by eta. Eta is the length scale, Kolmogorov length scale, right. Okay, so so now let me sort of write down here that it is really found, okay. So what we find by doing this exercise, right, is that well, let me just write that down here as an inference, okay. So 99.9%, right, So 99.98% of the modes represented, right, have wave numbers okay, that's one statement. So and okay, so let's just say less than 0.02%, right, of the modes represent the motions in the inertial subrange. Okay, so what exactly are we saying here? That KDI, right? So KDI is essentially this, right? So 99.98%, right, of the modes represented have wave numbers which is larger than KDI. So essentially so maximum, the majority of the dissipative motions actually lie within in that shell here, right, in that shell here, maximum. And in the inertial subrange, which exists somewhere here, right, it's about 0.02, less than 0.02% of the modes. Right? This is something that we know. So in that case, right, so what happens then? This actually then gives you the motivation to sort of reduce the resolution in the dissipative range, right, because most of the waves are in that zone, right. So that's the way the domain is, right. So now that we know all these things, right, what are things that we can do sort of alleviate the computational cost of DNS, right. So let us we basically will look at some of those things, right. So number one is essentially low wave number forcing. So let me write that down. So what I mean is some of those, what can I say? So we're basically saying that how can we, I think we said that in the previous class, that we're trying to tweak the existing DNS to see if we can alleviate the computational cost. So one of the things that you can do is right. So like we said that like we've said right here, that most of the modes represented, lie in the dissipative zone, right. It's a very small percentage of the modes which are in the inertial subrange, right. And those length scales are even like lesser than this. That's what we've just said, right. So one of the things that can be done, see, when energy is transferred, and we've talked about this earlier also, I think I've mentioned this earlier. So when energy enters turbulent flow, it enters through the largest scales of motion. So if you supply energy, it will first go to the largest eddies, and from there it will cascade down to the smallest ones, right. But what we do here in terms of low wave number forcing is supply that energy, but supply it directly to the smallest of microscale motions in the microscale length scale, right, which will probably be target some of these modes, right. So you directly supply that energy to those motions, right. Now this, of course, these are unnatural and they will not follow Navier-Stokes equation. Then what is the purpose? Well, you do not really get, you do not really resolve all of the motions by something like this. But because there are certain, properties of the inner smallest scales of motion, which are universal, right, which basically depend on viscosity and dissipation. This is something that we've said earlier. So, in the sense that the geometric definitions are lost, which is therefore larger eddies, right. So, and the path in which the energy is transferred, that also is lost. So, here the behavior at these length scales is very universal, right. So, because of that, so what we can get some, extract some kind of information from there, right. So, one of the things that is so essentially this is an artificial way, right, it's an artificial way, and you can get up to, you know, higher Reynolds numbers, right. And we've said earlier that the Reynolds number, so the number of modes that is required, right, it increases as the cube of the Reynolds number based on the turbulent flow length scale, or 6 times of the Reynolds number based on the smallest of the length scales, right. We've said that earlier. Now, so let me sort of write that down. Okay. So, what I am basically saying here is statistically, okay, stationary homogeneous turbulence can be obtained in DNS okay, by artificially forcing okay, the low wave numbers okay, yeah, by providing energy to them. Okay. So, in the sense that one of the things that is done to study the turbulence in this domain, now that we've seen this, is to provide energy, right, which will enter into that flow domain through the largest eddies. So, you provide that energy and now see what happens, how the energy is cascading, how the geometry is changing, and so on and so forth, right. This is typically what is done. So, this is another way of, where you do not provide the energy to the largest scales, but actually go and send, provide this to the smallest of length scales, right. So, these motions, so energy containing motions are therefore unnatural and do not follow Navier-Stokes equations. If you sort of, this is an artificial, so artificially forcing, right. So, energy containing motions unnatural and do not follow Navier-Stokes equations, right. And this doesn't, like I said, it doesn't really solve the whole turbulent flow domain completely, but it gives us some information. So, to give you an example of that, say, so n is the number of modes in each direction. So, okay, let me sort of do that. This is an example, for example. So, this is n, right? So n is essentially the number of modes in each direction, okay? Then total number of modes right. Now that is actually equal to n cube, okay? Then without forcing, with forcing, right? So I'll give you a couple of examples. In the sense, what is the maximum Reynolds number that I can actually look at, right? So because I think I mentioned last class that given given a turbulent flow, then the maximum number of R lambda, which is essentially the Reynolds number in the smallest of length scales, that you can get up to with gigaflop computers is 100. That's all. Right, but we want to get more. So here n is essentially the number of motions or say modes, okay, in each direction, right? So I have two examples here. So say n is 256, right? So total number will be 256 cube. So without forcing, the R lambda that is reached is 60. This is and the R lambda is 180, right? Now this is referenced in the book of Pope, and you can sort of look that up, okay? So this is an actual experiment that people have done, and this is the result. Okay. Then another is if n is 512. Okay. Total number of modes is this, right? And the max with forcing, the maximum Reynolds number that has been reached is this, right? So it makes a lot of difference. If I do this essentially, okay. Okay, so we'll make final comments when we get there. So this is one way, okay. All right. So what I'm basically trying to say here, kind of repeating myself, I guess, is that we have several motions, right? Like we said, in a turbulent flow, like we said in the last class, that there are length scales vary, right? Vary quite a bit. We have the Kolmogorov length scales, which are like really small, and then we have the larger eddies, right? Then we also have Reynolds numbers, which are widely variant, right? And then we have the wave numbers. So the wave numbers, and which is what we're seeing here, that if you take a domain which is of a diameter of 2 k max being the wave numbers of the highest dissipative motions. So then this is my domain, right? This is my domain which I'm looking at. It's a sphere of diameter 2 into k max or radius k max, and in this band which is shown in yellow, so most of the dissipative motions, or most of the motions actually lie here. It's only 0.02% of the energy containing modes actually lies somewhere here. It's the inertial subrange. So inertial subrange is located somewhere over here, and the maximum peak of the spectra, right, which we had also seen from the experimental distribution, is somewhere over there, right? So what would be the most, so the high, I guess all the kind of methods that we're looking at, so we're trying to see what, since these are distributed so randomly and they are not their distribution, there's nothing uniform about that, right? So what could we use, right, to sort of make the maximum, take the maximum advantage of that, right? So when we said low wave number forcing, so some of the things, so one of the things, the moment you see this, you're like, oh, so most of the waves are actually contained in this region, then we can have a slightly reduced resolution there, right? Because if I reduce the resolution somewhere here or here, then I might miss out, right? I might miss out on the wave. But this is more densely populated, so I can do that. So that's the kind of thought process, right? So now having this picture, so our job is cut out as to how we go and decipher or resolve all these motions. Right. So one of the things that one of the ways of doing that is what I described right now, is the low wave number forcing. Right. So you have these low wave numbers which are here. So you provide energy to them. Right. So you provide energy to them, and which is unnatural, and they do not follow the Navier-Stokes. Right. So then why am I doing it? Because it doesn't really represent the turbulent flow as such, but you can extract some information from there, right? Which is what we are doing, and we saw that I can actually get up to Reynolds numbers at the micro scales, which are much higher than without forcing. Right. Okay. Now the next thing is, of course, we are all familiar. Okay, LES. Right. So what do we do in LES? Well, in LES, essentially the energy contained modes are resolved, and the effects of the unresolved modes are modeled. As simple as that. Okay. So, in LES, the energy contained modes are resolved. Right, and effects of unresolved modes are modeled. Okay, that's your LES. Okay. There's something else. Another way. So another method, okay, is called hyperviscosity. Okay. Now what do we do here? Okay. So what we do here is we essentially replace the viscous term right. We replace this by okay. Okay. For integer m, right, and this thing is the hyperviscosity coefficient. Hyperviscosity coefficient. Okay. Now, what this essentially, how is this helping us, right? What this is, doing is in wave number space, right? This corresponds to changing, right? Right, this to right. So essentially this results in making the dissipative range making the dissipative or dissipative region narrower, right, makes it narrower. Okay. Such that you require less more, wave numbers to resolve. Lesser number of wave numbers are to be resolved. Right? So that's hyperviscosity. Okay. Further, we have still, even one more, right? So which is essentially the sparse mode methods. Okay. What do I mean by that? Okay. Let me write that down. Sparse mode methods. Okay. So here the energy containing modes are completely resolved, right? That is, so this is the region, right? So the energy containing modes in this zone basically, right, for R less than K, Ke, right? So that is completely resolved, right? So in sparse mode methods, so energy containing modes are completely resolved. So energy containing modes are completely resolved. Okay. And in shells of higher wave number, right, in this method, and for higher wave numbers, okay, okay, right, where this etc., right. And so essentially here only a fraction, okay, this has become a little congested, sorry about that. Okay, so energy containing modes are completely resolved, and for higher wave numbers, right, so essentially a fraction which is only a fraction of the Fourier modes are represented, which is only a fraction which is right, of the Fourier modes is represented. Okay. Right. So essentially that's all. Okay. So we have a DNS, right, and we think that if we can tweak, the DNS, or essentially we are trying to see how we can decrease the computational cost of the DNS, right, and so we've come up with several methods. Right. One is the low wave number forcing, the other is of course the LES, then we have something called a hyperviscosity, and then we have sparse mode methods. Okay. Now, but it's all of these things, right. However, so like I said, we will need to write something here, write a note, and basically say that all these methods, all these methods that I spoke about have, substantial deviations from the Navier-Stokes equations, right? And so they are nowhere near like direct numerical simulation, right, of the turbulence, and it's only a model. Okay, so let me just sort of write that down. It's important to appreciate that. Okay. All the methods substantially deviate, right, from the Navier-Stokes equations. Okay, and there's no way it is a DNS of turbulence. So they are not DNS of turbulence. Okay, and each is a model whose accuracy is not known, is unknown. I think that's all I will talk about the DNS and its cost and what we sort of do about that. Okay, so pseudospectral methods, as I said. So the point is that we did discuss DNS, right? It has a certain computational cost, and we are seeing how we can alleviate that, and we did come up with a couple of methods. And what we now see is that they actually deviate substantially from the Navier-Stokes equations, and definitely they are no way the DNS of turbulence. However, each is a model whose accuracy is also not known a priori. Okay, that's where we have to leave it, in the sense that then we make, I guess, judicious choices when we decide to study a problem. Okay. All right. So now, so I think where we are slowly inching towards now is to slowly go and see that how we can actually solve this. So we will do the CFD bit very soon, but before that, okay, I'd like to talk about a couple of models which you will see when you go to ANSYS, which is very popular, right? You use a turbulence model, right? You use the K epsilon model, K omega model, right? K omega SST model, right? So shear stress transport, right? You don't even know what that is. So I think what we will try to now do is slowly we inching there. You are hearing this word model, right? So we're going to resolve those, some of the wave numbers, and the rest of them we are going to model. I think this is something that we've said in the course of describing these things. So I think we're inching towards that, right? So let us sort of, now the point comes that, okay, now let's see. Today, of course, we have better computing facilities, better computing power, more importantly. So let us see, right, how methods have developed and what characteristic each one has, right? Okay. Let me sort of write down a few things, okay? We can sort of discuss again a little more in detail, okay? Let me go to another page, okay? So let me just write down these things first, okay? Okay, so the velocity, right, we wrote down as right. So this is the Reynolds decomposition, right, and then of course you have the continuity momentum and energy. So from continuity, okay, right. So which means right, and okay. Next, of course, we have the momentum equation. Okay, let me write this: the momentum equation and then the mean momentum equation. Okay, so let me. Okay, I think fine. Let me write that down. Okay, so just to remind you, so. So momentum equation is this, right, and I'm not sort of driving it further. We've sort of done this before. Now mean momentum equation then, right? So that is equal to see how that is different from the momentum equation. Okay. 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 So that's the mean momentum equation. Okay. So Reynolds equations basically now, right? How is this different from the Navier-Stokes? If I look at the mean momentum equation, we've said this earlier, other than the mean values, so essentially the Reynolds stresses get introduced, right? This we found that out. So Reynolds stresses is introduced, and also what we've seen earlier is that the kinetic energy, right, the turbulent kinetic energy is half the trace of the Reynolds stresses, right. So essentially turbulent Ke, right, which we are representing by just this K, right, this is equal to half the Reynolds stresses. Right. Okay, so if I write that in words, so the turbulent K is equal to 1/2 of the trace of the Reynolds stress. Now, we will do something called a turbulent viscosity hypothesis. Okay, let me sort of briefly today, because of the lack of time, I'm just going to write down the equations. We'll discuss this a little more in detail. So let me just write this down. So this is something that we know already. What I'm writing out so far. Okay, so what I'm coming to is this turbulent viscosity hypothesis. Okay. So what is this, right? What is this? So this was introduced by Boussinesq in the late 19th century, right? It's mathematically analogous to the fact that stress is proportional to strain, right? In a Newtonian fluid, it's linearly related, right? Stress and strain. So this one, it was introduced by Boussinesq. Okay. Is mathematically analogous to stress being proportional to strain, actually being linearly proportional to strain. So strain linearly in a Newtonian fluid. Right. So this was, like I said, it was okay. So I got this extra U, and this is not that. Okay. So introduced by Boussinesq in, like I said, the late 19th century, is mathematically basically saying that the stress is linearly proportional to strain in a Newtonian fluid. That's the an analogy, right? So the Reynolds stress, right? The Reynolds stress right. So this, right, Okay. So this is actually going to result in the diagonals. Okay, you know that. Okay, is proportional to the mean rate of strain. So this Reynolds stress is proportional to mean rate of strain, right? So that is that okay, this is equal to okay, okay. So if you see this, this is actually equal to 2 rho nu t, and this is something that we can represent that as S. So we have seen that, that's rate of strain. Okay, so okay, this, right, where is turbulent of eddy viscosity. Okay, okay, and essentially I can also say that effective viscosity right this plus turbulent viscosity. Okay. Now just one more thing before we stop. So now right, that is equal to effective. Okay. 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 So essentially this is the same as Navier-Stokes equation. Okay, let me write that down. It is same as Navier-Stokes, okay, except you of course in place of Q, okay, gamma effective in place of gamma, okay, and P is modified so this equation that I just wrote back here in equation 3, so in that, so what I can write here is actually, so from say 3, right, now that is equal to turbulent viscosity that, right. So, essentially in a simple shear flow, right, it's easy to visualize, right. What we are basically saying is that the shear, right, is nothing. So, this is exactly similar to what we have learned earlier. The shear is nothing but viscosity into velocity gradient, which is what we are doing here, except that you can see you are looking at the turbulent quantities here, right, and this is the turbulent viscosity, and then this is the mean velocity, right. So, let us just say what, yeah, so turbulent viscosity is this, right, and the effective viscosity is turbulent viscosity plus, and this is what we have been doing so far, right. Every property we write that as a mean property and a turbulent part. So, which is, I think, is being done even to the effective viscosity. So, we write that as the viscosity part and the turbulent part, right, and then kind of boils down to the same thing. So, that this is how your equation kind of changes, this is your momentum equation kind of changes. So, I think I should sort of write this down. Okay, we will discuss this a little more. I just kind of wrote down the equations first because they are quite a bit. Okay. So, let me just, I think I will call this as 4. Yeah, so if you see how the equation changes, so this is again, it is the Navier-Stokes equation, except that this is these are the modifications which we have done, if you see, right. Especially this is the gamma effective is here, and the pressure is modified in this fashion. Okay. So, essentially again, so this term, right, if I, so it essentially boils down to the fact that we are looking at shear, right. Okay, so I think we will stop here and take this up again in the next class. So, thank you.